Well, I'm just going to show you some more polar curves in this section. This one here then, r equals a theta. Well, this is a really interesting one because you definitely can't come up with a Cartesian form for that. Okay, so that's the pole. Well, what's going to happen? Okay, well, r this time is dependent on theta. What you normally do is, if you're not too sure, is you draw out a table of values. Okay, but I'm going to do that in the next example. With this one, I'm just going to talk you through it. Okay, when theta is 0, r is 0, isn't it? So it's there. Simple. Okay. Let's take another case. Okay, when theta is like pi over 4, r is going to be a times pi over 4. Okay, so some amount times by that. Okay, when theta equals pi over 2, r is going to be a times pi over 2. Okay, so it's going to be somewhere like that. Okay, when theta equals 3 pi over 2, okay, so somewhere there, then r equals a times 3 pi over 2. Can you see? Because a is constant, I mean, you can choose any letter, any number you want. Choose a equals 1 if it pleases you. I would, because it's the simplest. Okay. Choose a equals 2, 3, 4, any other constant you want. Okay. Choose a positive constant because it works better. Okay. Otherwise, we have to say theta is negative as well, because remember, r can't be negative. R is always going to be positive, so keep a as being positive. Okay. But if it pleases you, use a equals 1. Okay. So when theta equals pi over 4, pi over 2, well, I've got a feeling I said 3 pi over 2 in the video. I didn't mean that, did I? I mean 3 pi over 4. Pi would be here. Okay, and then can you see what's happening? You're actually sort of spiraling outwards like this. Okay, and then this will be 2 pi, you see, there. And then you'd have another spiral outwards. 4 pi, another one outwards, 6 pi. And just keep on spiraling outwards, and it's kind of rather nice. Okay, it's called an Archimedean spiral, named after Archimedes. Okay, not too sure why it's named after Archimedes, but there you go. There's so many things I'm not too sure of, but you know, I haven't got time to look everything up. Anyway, that's a spiral, and you can't do that in Cartesian coordinates, of course. Let me show you a couple of other ones. Okay. In terms of things I can memorise, that's it. I don't memorise the rest of them. So here, a 1 plus cos theta. You can see why I just don't have the inclination to memorise this. Not what the shape looks like. Okay. But what do you do for r equals a 1 plus cos theta? Okay. Well, this is where I'm going to show you what a polar coordinate template looks like. Here it is. Ta-da! Isn't that fascinating? All right, so you've got the pole here and the initial line there, theta is 0, and then you've got various angles for theta. Okay, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and so on. You can put more lines in if you wish, okay, but it's kind of handy for what we're about to do. Okay, so I would sometimes have a template like this drawn on the board, and I'd actually use that to try and work out what's going on. And we'll come back to that shortly. So I'll leave it there where I think you can see it. Okay. Now what I was going to say was, if you're not sure what's going on, you use a table of values. Okay. So I'm going to put theta and r. Okay. Why have I done it that way around? Well, theta really is the independent variable. Remember, you normally got Cartesian equation y equals something in terms of x. You've got x coordinates you put in, find the y values. Here you work out, you choose what values of theta you can have, and then you work out what r is. Yeah. So we have theta, and what we're going to do is we're going to choose some simple values. The simple values to choose are, well, obviously, I hope, 0, pi over 2, pi, 3 pi over 2, but I also like to choose other values as well. When there's trigonometry involved, I choose values like this: pi over 6, pi over 4, pi over 3, pi over 2. Alright? And you can keep on going to 2 pi. I'm just going to choose that for the time being, okay? And I'll work out what's going on here. So when theta is 0, cos theta is 1. 1 plus 1 is 2, so I've got 2a. Now, interestingly, that's the maximum value that r can be, isn't it? Because the maximum that cos theta can be is 1. And so 1 plus 1, 2a, that's the maximum value. So if I'm going to do my axes, okay, I don't need to have the initial line extending more than 2a if I was going to label the number of my axes, okay. Right, pi over 6. Right, cos pi over 6 is root 3 over 2, okay, plus 1. 1 plus root 3 over 2. What's root 3 over 2? 0.866. 1 plus 1.866. Right, so 1.87. Would you be happy with that? Yeah, of course you'd be happy with that. Pi over 4. Cos pi over 4. Root 2 over 2. 0.707 plus 1. 1.707. 1.7. Would you be happy with that? Again, of course you would be. Pi over 3. Thank goodness for that. An easy one. Half 1.5a. Would you be happy with that? Yeah, you would be. Okay, and pi over 2, whoo, another easy one. 0, so 1a. Yep. There we go. Okay. Well, what can we do with that? What can we do with that? We can drop our pen. That's what we can do with that. No. Let's do that. So look. So when theta is 0, you got r is 2a. So I'm going to put that there. And I'm going to say that this circle here has got a maximum radius of 2a, right? Then pi over 6. Okay, well, where's pi over 6 going to be? So let's use black. So that's pi over 4. Pi over 6 is somewhere there, isn't it? And pi over 3 is somewhere there, isn't it? Notice I don't bother labeling theta equals all the time, just for my own purposes. Here we go. So pi over 6, well, that's just a little bit under 2a, so it's going to be somewhere like there. Can you see how this is working? Okay, so I'm using the circle to give me an idea of the distances involved. All right. So the next one, pi over 4, is 1.71, so it's getting smaller, isn't it? And then what I want to do is end up with pi over 2a, which is halfway. That's going to be a, isn't it? So the scaling of that is just all sorts of rubbish, mathematically put. So I'm going to try that again, okay? It's what's going to be doing that, basically. That's slightly better. Yeah. Yeah, can you see that? Okay, it's going to be doing that, okay? So if that was 2a, that's a... Yeah, so it's giving me an idea of what's going on, okay? I'm looking at there for the moment, and I'm going to proceed with what's happening between pi over 2 and pi. So next, yes, these are time consuming. You might be able to set up Desmos in polar mode. I've not tried it, but you might be able to do it. So pi over 2 we've done. What will come next? Do we need to do it? Do we need to do it? I'm going to suggest to you not. Okay. Why am I going to suggest to you not? Okay. I'm just thinking about this. Yeah. This is what I'm going to suggest to you. This is what the cosine graph looks like, isn't it? So between 0 and pi over 2. And then between pi over 2 and pi is what I want to look at. Okay, that's the cosine graph. Let's just load it up properly. Can you see that between pi over 2 and pi, let's just put in pi, it's going to descend to its lowest value of -1. So that is going to be 0, isn't it? Well, what that tells me is that these numbers are basically going to keep on going down until you get to 0. That's what it tells me. Okay, and the rate at which it decreases is going to be the same, effectively, this way as it was that way in reverse. You see that? Yeah. Let's just save me a bit of time. Let's just save me writing out several values in the table. Rewind the video and play it again if you need to, okay? But the angles I'm going to substitute in, they're going to get smaller and smaller until I get to the smallest possible value, which is going to lead me to a value of r equals a. All right? Good. Right, so what does that mean then? Well, what that means is, by the time I get to pi, I'm going to have an angle of 0, which is there. So I'm going to have a radius of 0, which is there. Okay, so it's going to keep on getting smaller and smaller. It's going to spiral in until it gets to 0. It's going to spiral in this way. See that? Ooh, there. Isn't that nice? I can see what sort of shape this is going to be now. Okay, so that's that. Right, oh, let's keep it there. What I want to do now is look at what's happening between pi and 2 pi. Now remember, I did say that sometimes it's more useful to think of it as between 0 and negative pi. Yeah. For the cosine graph, what does it look like between 0 and negative pi? It's a mirror image, isn't it? Okay, it's a mirror image. Or we just consider this rather nice result, which I'm going to write down. That's cosine negative, let's put theta, is equal to cosine positive theta. What that means is, if I just change those to negatives, those values are going to be the same. Okay. What does that mean? What that means is, if I go the other way now instead, it's going to follow exactly the same pattern as at the top. In other words, what I'm saying is this horizontal line is a line of symmetry. Okay, so you can see the hard work is really just from doing it from 0 to pi over 2. The rest of it is just using what we know about the cosine graph. And this is why trigonometry is just so important, okay? Because we can use that fact to just know this is going to be a mirror image, and I'm going to just draw it in like that. It's lovely, isn't it? There's not a point there, so it's not how we would draw a heart, okay? But it is basically a heart shape, isn't it? Anyway, it's that. And what I'm going to do is I'm just going to draw it kind of nice enough on the board, because that was just drawn up bit by bit. How would we draw it? We'd have the initial line there, and then we'd have the heart drawn something like this. There, notice where my pen is in relation to the initial line. It's at right angles, isn't it? Yeah. Okay, yeah. So just make sure you draw it like that. I've got to try and get the symmetry right here. This is not a curve, I draw that often. Ooh. Stand back. Yeah. That's not my best one. But there you go. I'm going to keep it up. Okay. That's called a cardioid. You know, and you know, people in medicine, they use the cardiovascular system. Yeah, it means the same thing. It's all about whatever the Latin is for heart. But there you go. It's that. Okay. Yes, that's a nice curve in polar coordinates as well. I want to show you another one. Okay. I'll tell you what. No, I'll do it in another video because it'll take me time to rub this off and stuff. Okay. So I'll see you soon.